Okay, so the next derivative rule that we're going to be covering is called the power rule. Okay, and basically what the power rule says is if you have some function f of x equal to x to the n power, and n is equal to a rational number, then f prime of x is equal to that exponent n times x to the n minus 1. So basically the power reduces by 1, and then you pull out that n and put it in front. So now it's a multiple of that function. So what I'm going to do to prove this is we're going to need something called binomial expansion. Hopefully this is a review for you. But basically if you have some x plus h to some power, let's just say it's squared, then you can it works out in a certain pattern that when you simplify it, you end up having x to the n plus nhx to the n minus 1 plus this mess all the way down, depends on what your n value is, to h to the n power. Okay, so if you did it like with 2 or 3, it wouldn't be going that far, but if you did it with something like 100, then you would need this pattern. So we're going to need this binomial expansion to prove the power rule up here. All right, so here we go. The first thing we're going to start with is the derivative definition. So f prime x, you should know this by now, the last couple videos covered this. So what I'm going to do is substitute in f of x plus h. So I'm going to substitute the x plus h in for f of x, and you end up with something like this. So limit as h goes to 0, f of x plus h, it would be parentheses x plus h to the n power. I'm just replacing the x with x plus h to the n power minus x to the n all over h. Our f of x is equal to x to the n, so I just plug it in there. Okay, you should be able to see now why we needed the binomial expansion right here, because we have x plus h to the n power. So I'm going to use the first couple terms here in this expansion to solve this problem. So I end up having x to the n power plus, so x to the n plus nhx to the n minus 1 plus nh squared times n minus 1 x to the n minus 2 all over 2 plus, I'm just going to put the dot 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 there because you guys get the idea with the pattern, plus h to the n power. I'm going to put parentheses around all of this because that's just our first term here, the f of x plus h. We still need to subtract x to the n power, like so, and then this is all going to be divided by h. Okay, let's cancel some things out, simplify a little bit. We have an x minus n right here, minus x minus n, so I'm just going to cancel that out. Nice and easy there. Next, you'll notice that there's an h here, an h here, and an h here, and an h in every one of those other terms because it follows the pattern, h to the first power, h to the second power. Every other power would be in there as well. So these are all factorable. You can all divide, you can divide by h for all of these terms in here, which is good because we can't plug in 0 for h yet until we cancel out this bottom term. So that's what I'm going to do now. I'm going to cancel out here. H cancels. This becomes just an h not squared, just h to the first power. And then we'll just leave that there for now. We don't need to worry about that. Now we should be able to plug in the 0 for h because we're not dividing by 0 anymore. So if you plug in 0 here, this term stays the same. But this term right here, because it has an h, all of that would cancel out because of the 0. So that doesn't exist anymore. H to the n power, well, we can plug in the 0, so this doesn't exist anymore either. Neither does anything in between. So I'm just going to put a line through that. So the only thing you end up having left here is this nx to the n minus 1. So because I plugged in the h, I don't need the limit anymore, so I'm just going to write nx to the n minus 1. And if you look up here, that's exactly what we were trying to prove. F prime of x equals nx to the n minus 1, which it says up here. So this basically proves what the power rule is. If you have any questions about the power rule, let me know.